Howdy, hackers, and welcome to another episode of FairLight TV. There's been a bit of a break since my trusted desktop computer broke, but we are back, and this time we are going to discuss the topic of the C64 keyboard. How does that work? So, over to the keyboard. So the C64 keyboard, but just let me say something first. There was a recent comment in one of the episodes that, oh, well, for the first time I found FairLight TV. It's really annoying that the search algorithm didn't point me in this direction before, which for me is really distressing. I've been doing this for well over 2.5 years, and it's really, really sad if people don't notice it. So I'm not saying this is for everybody, but please do your little piece here and share with people who might be interested. We're not going to pest people who are not, but do ensure that all who could be interested are aware. That's every bit of nagging I will do. So let's get over to the C64 keyboard. So a number of years ago, it's like 4 years ago, that I wrote a blog post on my personal blog, which is sort of a waste bucket of everything that's sort of tech related. And then I put a reference to this on my LinkedIn page. I don't usually mix my sort of professional life with my personal interest, but this is sort of an exception, so I did that. And much to my surprise, Fred Bowen replied. So, and his reply was, your fun is discovering how it was implemented. My fun is watching you discover how we implemented it. And it was fun to figure out how to implement it around 40 years ago. Fun echoing all around again and again, lol. So, and looking back at Fred's CV, he was a senior engineer at Commodore Business Machine. So he was one of the guys that was responsible for actually making the C64 keyboard. This is probably one of the coolest comments I have received on any of my posts on LinkedIn. So thanks, Fred. That was awesome. Okay, so let me try to break this down to you. So the keyboard has sort of the physical layout and the pictures, or the images that you see on it, characters, and also the symbols and all of that. And then there is the registers DC00 and DC01, and we will go through that. And then there is a kernel matrix, and we will go through that as well. And then the actual picture that you would see on your screen is based on the character ROM, and we will go through that as well. So this is when you press a key, you yield something that shows up on the screen, and the entire process is like this. So let's go through each of the steps here. First, the pictures on the physical keys. So this is a regular C64 keyboard. You have seen a bread bin a number of times before, I'm absolutely sure. So here you would have keys with symbols on top of them, so your characters basically on top, but you also see the symbols on the front, the graphical symbols, the sort of the Petsky symbols. But if you take a look at the Swedish keyboard, it would be something like this. So you see here the O, Ä, and Ö, so the A with the circle, the A with 2 dots, and the O with 2 dots. So that's distinctly different from a regular US keyboard. And if you take a German keyboard, you would have a swap between the Y and the Z. So they don't have QWERTY keyboards, they have QWERTZ. Look at the German keyboard and you will see that. The physical keyboard is the same. So it's just the pictures that change. So electrically, when you press a key, that would always yield the same output. So it's not so that they sort of implemented the different national variants by changing the layout and the cabling of the keyboard. They are always the same. So this is where we get to DC00 and DC01. So the keyboard matrix is connected to the CIA, one of the timer chips, the first timer chip, where DC00 is one register and DC01 is the other register. So the way you validate the key presses is that you put a value in DC00 and then you get something returned in DC01. There is also a data direction register here. So you put an FF in DC02 and you put a 0 in DC03. That is to ensure that one is all in and one is all out. And I don't know which one is which, so I'm skipping that part. But what you do is you put a 0 in one column at a time. So the key scan routine of the kernel is putting a 0 in bit 0 and then validating any hits on that one, a 0 in bit 1 and then testing for the hits in that, and then going that all the way to bit 7. So that is validating each of the 8 bits and then seeing if there is any of the 8 possible hits on that row. So, and again, I just like to ensure that you get the difference here, that whatever picture you see on the keyboard doesn't matter. They are all sort of electrically the same. You need to ensure that the DC00 and DC01 is converted into something that corresponds to what is actually printed on the keys. And this is done using the kernel matrix. I've scanned my Commodore 64 whole memory guide, the ultimate Bible, the only one you can actually trust, which is not filled with fictitious stories. So here you would have 4 different matrices. One is if you have pressed just one key, an unshifted standard key, and that table is placed in the kernel memory on EB81, so it's 64 bytes there. And then you have a shifted one, which is on EBZ2, and then you have, if you've pressed Commodore and one of the keys, that is on EC03. And then if you've pressed Control and one of the keys, that is in EC78. And so the standard portion is down on the lower left. If you, let's say, if you put a 0 in the lowest bit of DC00, and then you read what comes out on DC01, and you read FE, that means that you have detected that the delete button has been pressed. So you poke FE in DC00, and then you read DC01, and you get an FE, that is delete. And here you can also see that you can detect joysticks. And this would be on port 2, so DC01. And that is sort of the confusing part, because if you're using port A, or the first port, that would mean that you need to read from DC00, and that is sort of the confusing part. Whereas if you have the joystick in port B, you would have the data direction set so that if you press certain keys, they would be the same as the joystick pins, because the joystick pins is sort of checking the bit 7 here. All the joystick direction is the same as checking the corresponding bit 7 characters on the keyboard here. So you would see here 1, left arrow, Control, 2, and space. And you might recall that if you connect the joystick to the keyboard and just fiddle with the joystick in port 2, you would see these keys being echoed on the screen. So the keyboard scan routine sees your joystick movement as key presses corresponding to the data direction, corresponding to these hits here from bit 7. So that is one aspect. Poke in DC00 and then read to DC01. Ensure that the data direction is set properly. So FF in DC02 and 00 in DC03. Was it? Yes, that was it. Right. And here is also where you have the national variants being adjusted. So ensuring that what is the picture on the physical keyboard corresponds to the picture, the PETSCI value that the system picks up. You have these tables, and this is the unshifted version from a US keyboard. That is, of course, what the Commodore whole memory guide has as a default. And then I've also sort of typed the what is in the Swedish kernel. So a Swedish adjusted kernel would have the scribbly notes here. Some of them are, of course, the same. So you see here the AB A9 is 2B, and here it's 2D, but the next one is 40. The next one is 4C, and those two are the same. So it's not like they've randomly placed every character around. It's just the number of characters are changed, and yeah, so this is the change. All right. Yeah, and I could make you aware of this one. So if you have your Commodore 64 whole memory guide, you might want to change this here. That is supposed to be BF rather than whatever is there. All right. So digging around in my, I should say old disk, but it was actually on a USB stick that's on my Ultimate 64. I found an old program that I seemingly coded, but I really can't remember. But yeah, it says my name, so I'm pretty sure I did it. So let's run that one. It's called Key Matrix 1.1, and this is a program where you can press keys on the keyboards, and it will tell you where on the DC00 and DC01 matrix that character is placed. And I guess it's also showing the the PETSCI value for that character. So if I'm pressing here QWERTY, yeah, that should be the values for that. So what you see here is actually a program that pokes something on DC00, and if there is a hit on DC01, it shows an asterisk where that hit is. And seemingly I did this to validate Vice, so because I was fiddling with the key maps on Vice to ensure that there was a Swedish key map available. So, and this one is also, let's keep the normal joystick. So I have, I don't know if you can see it, but the little field down here that shows the direction of the joystick. So if I'm pressing joystick 2, as we established, that will give a result on DC00, but my program does never read DC00 because it pokes to DC00 and then reads from DC01. So nothing would happen there. But if I'm swapping joystick, and this is just a convenient way to ensure that the keyboard joystick now sends to port the other port. Here you can see that when I'm pressing here, so this is up, that gives a hit in column 1. But since my program is poking something on DC00 and then reads from DC01, you would see the asterisk being represented at the time where it gets a hit on DC01, but the joystick doesn't need any input from DC00. It just gives the result on DC01. So that's why you have the hits on the entire column here. So this is up, here you have down, here you have left, and here you have right. And I guess this, which one? This one is the fire button. So there you go. You would have up, down, left, right, fire in the column 0, 1, 2, 3, and 4 on DC01. Of course, I could expand the program to have some sort of assumed joystick detection also for the other port, but that was seemingly not part of the program. But This piece of code is available on CSDB. It's key matrix 1.1. Here I have a space between key and matrix, and I think the name I gave it on CSDB was they were sitting together, so it was key matrix as one word. Well, anyway, feel free to download this if you want to validate your keyboard. So now the system sort of picked up your character, went through the so the interrupt where the key scan routine has scanned DC00 and DC01, and it has fetched the PETSCII value of the key that you pressed. The next thing is that what you actually see on the screen when you print that character is what is in the character ROM. And given that, I mean, there are more characters with national variations than you can kind of fit, because they are all occupied in a standard in the standard font. So so the national variants basically needs to hijack some place of the character ROM and replace that with your national characters. So if you see here in the orange square here, you have the brackets, the square brackets, and the Libra sign, so the pound sign. They are the ones that were changed to this A with a ring and an A with 2 dots and the O with the 2 dots, the Swedish variant keys. And I'm sure the similar approach has been taken with all sort of national variants. You needed to hijack a few of the original characters in the original character ROM and make national variants and poke them into the character ROM, and then also ensure that they corresponded to the right key by having that in the key map. So international adaptation used 2 methods. One is the kernel key map, which makes sure that the keys are structured as they are in the national standard keyboard. And then you also have the character ROM to ensure that the national characters are there in the corresponding location to where they are expected in sort of your national variant of the PETSCII table. There is a special case here, and that is emulators. That adds even more complexity to this, because when you have Vice as an example of an emulator, you have national keyboards, so you have somebody, the OS is running the character, is detecting your character presses, and then that is fed to Vice. So Vice is already fed with a number of characters from your keyboard, and then it processes that via a file type which is called VKM. So that is basically the glue that sits between your OS detected characters and the DC00 and DC01 inside your Commodore machine, the emulated Commodore machine. So you have to have a VKM key map file that corresponds with the kernel, the key maps in the kernel. Otherwise, you would have you would be pressing one key and you could get a totally different result inside the emulated machine. And if you don't have any definition or anything like that, you would always be, or Vice is always assuming that you are using a US kernel ROM. Otherwise, it would be very, very complex. So that is sort of what the Commodore keyboard works like. It's not that difficult. Poke in DC00, read to DC01, and then use that to detect which of the options in the key map that you have pressed. And the easy part here is that you store a 0 to all the addresses in DC00. And then if you read from DC01 and you get an FF, that means that no key has been pressed. So the easy part is just read DC01. If that one is FF, likely no key was pressed. That is sort of the simple use case. Normally you would have press any key, and that would be implemented as LDA00, STA DC00, and then LDA DC01, CMP with FF. If that is true, then no key was pressed. That was everything I had for today. It's very brief, but just to ensure that we had a regular Friday launch starting again, now that my computer works again. Thank you so much for watching, and see you next week. Bye bye.